This is Dr. David Brown from Pellissippi State Community College. This podcast is about hexadecimal. The assumption is that if you're watching this podcast, you already understand binary. The reason why we study hexadecimal is because hexadecimal can be used as a shortcut for, or a shorthand for binary representations of numbers. One hex digit, as you see over here in the text to the right, can stand for 16 different things. And in hexadecimal, which is base 16, the 16 symbols are the numbers that we're familiar with, 0 through 9. There's also this odd thing of there's letters in the hexadecimal representations, but the letters A through F are also used to pad this out to 16 symbols, with those letters standing for the numbers 10 through 15. So A is a 10, B is 11, C is 12, and so on. F is 15. So these are the way numbers in hexadecimal are represented. So that if we had, let's say, a number in hexadecimal like, let's say 1C, base 16, hexadecimal. This is how we specify that something's in a specific number system, is by using it as a subscript. And try to figure what that is in base 10. We should be able to do that using our symbols and place values, a concept that we talked about in the last video. In hexadecimal, the place values are, of course, since this is base 16, it's 16 times the one before it. So this is the ones place and the 16's place, and this next one would be 16 times 16, which is 256. So here we have a 1 in the 16's place, so that's 16. And C, as we said before, C is a valid hexadecimal digit. It stands for 12, since A is 10 and B is 11. So 1 times 16 is 16, and 12 times 1 is 12. So 16 and 12 is 28. So in hexadecimal, the digits stand for numbers in base 16. But the reason why we look at hexadecimal is because since each of these symbols can stand for 16 things, it just so happens that 4 bits of information in binary can stand for 16 things as well. And we can see this by just putting the place values here, adding these up. If we put all ones here, the biggest number that we can represent in 4 bits is 8, and 4 is 12, and 14 and 15. So the biggest number we can represent is 15. The smallest one we can represent is all zeros. So 15 things plus the 0, we can represent 16 different representations using just these 4 bits, 16 things. And so since one hexadecimal digit can do the same thing, we can actually expand these hexadecimal digits into 4 bits, and that's the key to converting between the two, so that 4 bits of binary stand for and can be represented by one hexadecimal digit. Let's kind of look at how this works. Let's say that we have a number in binary and we want to convert this to hexadecimal. You might ask, why would you want to do this? And the reason is, oftentimes we do need to look at data at the lowest level of the computer, like data that's in memory, or more often data that's being communicated, some kind of communications traffic, and you want to see what the data is. To look at the data as ones and zeros, that's hard for human beings to do. To just see long strings of the same repetitive numbers, that's difficult for humans to remember or to make any sense of. It's easier if we could have shorter strings of more encoded kinds of information, so that instead of having this long string of bits, if we could encode this as something shorter. And that's what hexadecimal allows us to do, and here's how we do it. Since 4 bits of binary equals 1 hex digit, we can just divide it up into groups of 4, and we're going to start from the right and go 4 bits and then divide it. Now this one doesn't have 4 bits, but we can always add zeros to the end to pad this so that it's even. So the number that I'm looking at here is 1011101, and I want to know what that is. This is the base 2, and I'm asking what is this in base 16. the way you do it is take this group of 4 bits and turn that into 1 hex digit, since 4 bits equals 1 hex digit. This 4 bits, that's the 1s, 2s, 4s, and 8s. That's 4 plus 1, that's a 5. Okay. Now let's take this other 4 bits here and turn this into 1 hex digit. That's 8. That's the 1s, 2s, 4s, and 8s place. So 8 plus 4 is 12, plus 1 is 13. Okay, so turn that into 1 hex digit, again with A through F representing the numbers 10 through 15. What we said here is this is 13. That would be a D. So this is represented by D. So the hex number that encodes the same number as binary is 5D hex. And the way we converted from binary to hex is by grouping it and grouping the binary number into groups of 4 bits starting from the right and turning that into just 1 hex digit. Now if you go the reverse direction, if we had, let's say, a number in hex like we started with here, this number in hex, and we want to know what that number is in binary, you can do the reverse process. We can turn this into a group of 4 bits instead of just the 1 hex digit. So a C is 12. 12 in binary is 8 plus 4 and no zeros and no 1. So there's the C. And a 1 in 4 bits, that's easy. No 8s, 4s, 2s, just a 1. So we're saying that 1C in hex is equivalent to this number in binary, and we can convert both these to decimal to find out. In base 16s, this is the 1s place and the 16s place, and we've done this a minute ago. That's equal to 28. Base 10, 16 plus 12 times 1, so that's 28. Okay, let's look at this in binary. That's the 1s, 2s, 4s, 8s, and 16s place. So 16 and 8's 24, and 4 is 28. So this one also equals 28. So both of these numbers represent the same number, just in a different number system. And that's the way we can convert between those. So instead of looking at this string here, 0, 1, 0, 1, 1, 1, 0, 1, we can instead just say 5D, and that means exactly the same thing. And you can see why it's easier to remember, it's easier to work with, and that's why hexadecimal is used as a shorthand for binary. So that's the end of the podcast. Hope you enjoyed it.